Good morning, everybody, and welcome to the session on cloud-based artificial intelligence and smart monitoring. I'm Annabelle Volgman, and I started the Rushhart Center for Women in 2003 after being an electrophysiologist for a decade. I decided that there was a need to focus on women and heart disease because the mortality from cardiovascular disease was underappreciated and women were being undertreated. And Dave knows me from a long time, so he knows my passion. So we have today some great speakers and panelists. I'm going to introduce them. First, Dr. David Albert. He is a physician, inventor, and serial entrepreneur who has developed life-saving technologies and products, turning a number of these innovations into tech startups. Today, he is a founder of 3 technology companies, Innov Alarm, Lifetone Technology, and the famous AliveCore. His latest invention, AliveCore's cardiomobile personal technology, became a global sensation via a YouTube video in January 2011 around the Consumer Electronics Show and was featured on ABC, CBS, CNN, and Fox News, among many other media outlets. Dr. Albert has 72 issued US patents, a large number pending, and several new secret inventions in development. I wonder if he can tell us about those secret inventions. Maybe not, huh? Okay. Dr. Roger Eng is a cardiologist at Virginia Mason Franciscan Health in Seattle. He trained at the Johns Hopkins Hospital with Dr. William Gurneau, renowned for oral hydration therapy during the cholera epidemics in the developing world. Dr. Eng completed his residency in Massachusetts and was selected as chief resident. He pursued new therapy for atherosclerotic disease and heart failure by recreating the human heart with nature's own scaffold and successfully regenerated the first human heart with reprogrammed iPS cells at the MGH at Harvard. He co-founded Charismo to bring AI to fight diseases at the global scale. He worked with Dr. Longo, the editor of Harrison's Principles of Internal Medicine, and Sherry Ling at the National Institutes of Health on one of the longest running longitudinal studies on aging in America using advanced computer vision. He worked at Kinsman Laboratory of Neurological Research at the University of British Columbia to understand learning, memory, and healing processes of the brain. He presented the Any-Scale Artificial Intelligence Summit 2021 and conducted an international pilot in the South and Southeast Asian countries utilizing AI to assist physicians in managing critical COVID patients at home due to hospital bed shortage. Love to hear about that too. Tatiana Canzavelli. Welcome, Tatiana. She is the non-medical person here. She has gone from a programmer to senior executive at Big Five to founder and CEO of a startup company along her 20-year career, recognized as a thought leader, mentor for her ability to guide Fortune 500 and startup companies through business challenges. She's worked for major companies like PricewaterhouseCoopers, Fujitsu, and startups in the early days of the web. Tatiana has personally helped companies jump from 0 to millions in revenue, even during the toughest economic times. She opened new verticals and markets. Today, she is the founder and CEO of Open Health Network, the startup in big data, blockchain, and artificial intelligence in the healthcare space. Patient Sphere by Open Health Network has been featured in VentureBeat, Mobile Health News, and other prominent publications. She's also a fierce chess player, so be prepared if she asks you to play chess. Dr. Maulik Majmudar is a cardiologist and chief medical officer and co-founder of Bioformus, a rapidly growing virtual care delivery and digital therapeutics company. At Bioformus, Dr. Majmudar leads product data science, clinical operations, and clinical affairs functions. Prior to joining Bioformus, he was a medical officer at Amazon, responsible for development and launch of Amazon Halo, Amazon's first health and wellness-focused membership service. Dr. Majmudar was also associate director of the Healthcare Transformation Lab at MGH and an assistant professor at Harvard where he was responsible for the identification, validation, and implementation of digital health solutions to improve healthcare delivery, as well as the patient and provider experience. While at MGH, he was awarded an educational grant from the Aetna Foundation to launch a fellowship in healthcare innovation aimed at fostering the next generation of clinical innovators. Welcome, Malik. And last but not least, Dr. Viet Lee has 2 bachelors in integrated life sciences in microbiology and neurosciences and computer sciences from the University of British Columbia in Vancouver. Viet founded a bioinformatics company in 2002 that developed the software to visualize the 3D protein structures from the hepatitis C mRNA strand with active sites for protein modeling. Working with Dr. Roger Eng, Dr. Sherry Ling in the NIA within the NIH, he and his team developed software to extract data from hundreds of thousands of DEXA scans from the longest longitudinal aging study in the world. This research led to a better understanding of osteoporosis, bone density, and matrix depletion over time. The technology developed was based on modeling templates of bone outlines and automating bone model augmentation to fit the bones of interest using their proprietary Gaussian edge detection technique and deriving bone characteristics from the X-rays. Well, as you can see from their bios, the panel is an amazing group of people, and I wanted to share all that because it's relevant to what we're going to be talking about today. So I'm going to start off with the first question to Roger. Dr. Eng, you told me that DeepMind, which is a game, began with games and led to beating a world champion in the game Go. I still haven't figured out that game, but tell us about what's the significance of these milestones for medicine and cardiology and why we're talking about this.
Excellent. Thanks, Dr. Volkman. It's a pleasure to be here. I think Tatiana will know very well the mastery of those games, incredibly strategic. And actually, I see a lot of those games actually having a lot of analogy in medicine. A lot of the times we do risk prediction, particularly cardiology, when even at really the initial onset of the patient, either in the emergency department or in the clinic, we actually already beginning to predict how high risk these people are. Basically, how I see it was several of my good friends, including Viet, really taught me is that these particular board games are really teaching us how to be moves ahead of the game. And in intervention, when we studied intervention as a cardiology fellow, that is exactly what we do. We try to be able to predict what would happen if we did the intervention, and then steps after that, what we need to be doing for the patient. Is it going to be beneficial for the patient? And that is really what it really came down to when Viet and I began to first look at how these things would work actually in life sciences. The second aspect of games is probably incredibly important. Something I think all medical students have studied is actually also yourself, Dr. Volkman, who has been an incredible academician, is the ability to develop research models at an incredible pace. One of the influential authors I've studied in my past, in my youth, that has really informed the work that I've been doing was Stanley Prusiner, one of the clinicians that actually did the research and the discovery of prion disease. What he did was, in the very beginning, when they were studying prion disease required a long half-life to mature and grow in bigger animal models. So he initially switched that to a much smaller animal model, the hamster model. This is also something that eventually became dear to me because we were running a lot of these heart failure models at Mass General, and we were actually using models that are even shorter than that, from 16 weeks in hamsters all the way down to about 9 weeks in rats. In games, it's even more incredible. In games, you can literally complete a single episode in approximately a few seconds. But that actually wasn't enough. So as we would learn is that these gaming models actually begin as almost like a tutorial, like the Hello World that we all, Viet would know very well when we begin training in computer science, of how to do artificial intelligence. So artificial intelligence took, particularly for a cardiologist that is not a programmer with the background, it really took us a lot of sort of trial and error to get there. But what these games were actually able to do was able to rapidly help us develop so that we can actually understand and troubleshoot all the little various hurdles along the way, and then be able to apply those learning models into the real setting. As we figured out when we were learning is that there were a lot of issues with trying to scale those models into big data. something I think Dr. Majmudar would know very, very well, dealing with really, really large data. At the NIH, it was actually very similar, but at the NIH, we were dealing with much slower algorithms. Now, with the algorithms that are incredibly faster, they actually gather hundreds of gigabytes literally in a matter of a few seconds. And so that became some of the initial stumbling blocks that we probably would have not known if we just jumped straight ahead into the real world clinical medicine world. And so I think games really help inform us really well is that we can go directly from beginning to end with these models, learn whether or not we have a model that generalized, and then immediately bring it to the real world setting. And we can show you that later.
Thank you so much. That makes so much sense. I'm going to ask Malik, can you talk to us about the evolution of algorithms? Following up on what Roger was saying, tell us how you use algorithms from diagnostics and monitoring to patient management.
Yeah, great. Thank you, Annabelle. Great question. And Roger, great points there. I mean, the one thing to keep in mind for the 2 points you made, Roger, right? One is you need the ability to simulate very rapidly and with a number, almost an infinite number of permutations or inputs in these models. But at the same time, the challenging part between games and humans is that confounders or personalization at a per patient basis is infinite number of possibilities. So the question is, how closely can you approximate the real world scenarios? And that's the research we have to do, right? So in terms of the evolution, though, I do believe there's an interesting time here, which is that majority of the AI machine learning models, for the most part, being focused very much on disease diagnostics or disease monitoring, which is physiology or things like that. But I think we're also seeing an evolution of that into more disease management, which I think Roger alluded to as well, which is, can we start incorporating care pathways, medications, labs, other aspects of clinical care, and have models try to assist clinicians or augment clinicians in disease management. If they do that, the reason I am very passionate about this field is there are two gaps we can fill quickly. One is standardization. As we know, there's so much variation in care nationally and globally. Can you drive standardization by virtue of quality? And the second is, as clinicians, we always focus on the clinical outcomes. We often forget the operational efficiency side of the equation. You could have phenomenal clinical outcomes requiring a lot of human capital, which is just not practical or scalable. So the other advantage of these models is to actually bring a level of resource efficiency. That can you go from a doctor or a nurse caring for 50, 100,000 patients to 1 to 10,000 patients. And that ability to scale now brings the cost down, and it allows us to scale. So I think those are the two aspects of this evolution from just disease diagnostic monitoring to more disease management can allow us to achieve both standardization, higher quality care, lower cost of care.
Thank you so much. So I'm going to turn to Dave. So how is a LiveCore, which I think everybody knows, it's was a big innovation that was disruptive innovation, for lack of a better term, in the care of our patients to detect atrial fibrillation. And I mean, every single scientific session that has been done in the last few years have talked about, screening for atrial fibrillation. And I think that it definitely has increased our ability. All of these innovations have decreased our ability to detect atrial fibrillation. Unfortunately, we still have to do the clinical work of trying to figure out whether that translates to decreasing stroke risk, which, is the ultimate reason why we're doing this. But how is a LiveCore, your company, using AI for specific clinical problems? And what is your take on all the monitoring that we're doing for opportunistic AFib monitoring?
Well, thank you, Annabelle. I would just say, first of all, to follow on what Malik said, yes, our devices are used for opportunistic screening. Yesterday, there were several of the papers, one from Greg Marcus, the iStops, where he's talking about, N of 1 studies, AFib triggers. But I think more importantly, and again, this is to Malik's notion, is management. We have a lot of treatment options, whether it's ablation and different types of ablation, whether it's pharmaceuticals, whether it's lifestyle intervention, and people like Price Sanders showing great results. We have a lot of different tools in our tool chest. But the reality is, what's the clinical outcome? It used to be, for those who are old as I am, AFib was the low back pain of cardiology. We would treat people with, we'd slow their heart rate with DIG, and we'd treat them with warfarin. That was it. And now we have so many treatment modalities, but the question is, how much of a big impact? We have better anticoagulants, the direct anticoagulants. We have ablation. We haven't really moved the needle much on antiarrhythmic medications, however, in a long time. So, what we've got to do is monitor our progress. You do an ablation, 6 months later, the question is that person going to go back into AFib? Well, in many instances, they will, or in a year, or in 2 years. Because while AFib begets AFib, the process that generated the ablation, the atrial fibrosis, is still probably going on if you haven't impacted the physiologic milieu. So I see our technology much more than diagnostic, but for monitoring the progress as we try to find that mixture of therapeutics that actually makes an impact on stroke, that makes an impact on ultimate heart failure, which, in heart failure, AFib is a bad confounder. And so this is the reason why we'll have personal monitoring. The other one is, you've got to get these people engaged in their own care. If they're going to change their lifestyle, you got to motivate them. And they want feedback. Copays and deductibles and costs are only going in one direction. And therefore, people want to be responsible. We have to put some responsibility in their hand. And that's where personal ECG devices, personal rhythm monitoring comes in. So I see the AI part of it is because this has created a deluge of data. Steve Lebitz at Mass General did a big study, many tens of thousands of ECGs from tens of thousands of patients. Having a Mass General cardiologist overread those is just not practical. It's not scalable, as Malik said. So we have to have AI do that. And we at AliveCor have been fortunate. We have well over 100 million ECGs, and that enables us to generate really good models. And so I would tell you, we see AI as a tool. Somebody said, is AI going to replace doctors? No, doctors who use AI will replace those who do not.
I love that, Dave. I think that you're absolutely right about what we are trying to do with detecting atrial fibrillation. Maybe it isn't the ultimate goal is not to prevent stroke, but to engage the patient in taking care of their whatever is causing the atrial fibrillation. If you can detect a small amount of AFib, which may not translate to a stroke, but if you figure out what it is that's causing the AFib, whether it's alcohol or sleep apnea. I love the iStop study because it showed that alcohol, again, if it hasn't been made clear to us that alcohol causes atrial fibrillation, I think this was another study that showed that.
Well, the good news is we can drink coffee.
Yes, I was going to say, yes, coffee does not increase AFib.
That red wine is a no-no. So thank you.
Exactly. Coffee does increase PVCs though, and decreases sleep, which, I'll take. As long as I have a normal heart, I can take the PVCs. But AFib is a different story, right? But I think you're right. Maybe what we should focus on in these opportunistic ECG in the younger patients, especially, and we should start at the younger population, is what is causing their atrial fibrillation. Because once they have persistent AFib, it's much harder to decrease because their left atrium is remodeled and it's a done deal. So I think that is maybe what we should focus on, is using these monitoring to change the lifestyle and change the way people are conducting their lives to decrease the risk of AFib and decrease the risk of stroke. All right, we heard your dog, Dave. Anyway, Tatiana, I'm going to turn to you. with all this medical talk, we talk about the importance of remote monitoring, but we also know that doctors don't have the time to review massive amounts of data that different wearable and devices sensors capture. What are your thoughts on this after all this conversation about monitoring?
Thank you. That's a great question. And before I get into that, I want to first thank AHA for inviting me to participate in this panel. Secondly, a comment on the gaming and data and all of that. So as I was a professional chess player for a good portion of my life. And despite the fact that I've learned, the basics of chess and opening and, everything else, I spent significant amount of time learning the game of each player I was supposed to play the next day. Why? Because personalization is extremely important. You're playing against a person. And the reason I mentioned that is it's important in healthcare as well. And you can have tons of data, predictive modeling, everything else, but if you are not including data from environment, socioeconomics, and then also figure out psychological state and how to motivate people to do things you want them to do, everything else fails. Right. So when we talk about, remote patient monitoring, and we just, released a special edition of Patient Sphere for cardiology with amazing results. But what we're trying to do is to look at all the aspects of healthcare. So you have a, healthcare team those people are extremely busy. So the amount of data that we can get and capture, and we are from variety of different devices and sensors. In some cases, our patients, they use 5-6 different devices, clinical grade and consumer grade devices, as long as data that come from sensors, such as noise level, humidity, and everything in between. We need to figure out how to make all that available to the care team in a way that it's actionable and integrated in their, day flow. So we spend a lot of time developing all kinds of algorithms and triage functions that indicate potential escalation of the disease, and then we also try to put it in the context of the patient, right? So any type of data taking out of a context where, how, and what happened, they also, can lead us to wrong conclusions. So the trick is how you take all the data that you can get and make sense out of it, and and take it back to the care team, help them to give options like Dave rightfully mentioned. We're not expecting algorithms to replace physicians, but we need to be able to potentially generate maybe 2-3 hypotheses on personalized, care plan that's applicable for this specific patient. And the specific patient means the all kind of data about that patient. And what I'm excited about, you all mentioned the things that excite you. I'm excited that we're getting with some of our clients to the point where we creating a digital twin. So we're taking tons of data, and it's 360 degrees data, including claims, environmental, socioeconomic data from everywhere else. And we're creating a digital twin that can be used for a variety of different things on prediction, potential modeling of treatments, and everything in between. So super excited, and we're doing AI at the right time in healthcare. So applaud to all of you.
Well, thank you so much, Tatiana. It is very exciting. And, as a physician, as a cardiologist, we welcome any help we can get to try to understand what we're supposed to do with patients. A big problem that we have is readmission for heart failure. We should be looking at technology that can help us figure out, is it social determinants of health, socioeconomics, that is really causing the problem and not really the disease. And if that's the case, then we should change the way we approach heart failure. So, I think we need to be innovative in using these technologies to really help not just the patient, but the hospitals and the country really to decrease the cost, the burden of some of these cardiovascular diseases. So thank you for that. I'm going to ask either Roger or Viet. Viet hasn't had a chance to talk, so I'm going to ask either one of you to comment on this. Google trained the earliest of the transformer models for language understanding called BERT. Can you explain that to us? It's a bidirectional encoder representation from transformers. How is this BERT technology? How can it be used to advance medicine and cardiology and research in clinical practice?
I can take that. That's actually kind of near and dear to me, actually. Exactly as you said, Annabelle, the social determinant of health, all the different factors that we as cardiologists actually weigh in for every particular patient, those are actually things that are typically hard to replicate, pretty consistently and precisely for every single practice, right? And then exactly what Malik said is that what we want to be able to do is standardize the care as much as we possibly can, because as we have learned, if we're able to standardize care, we can actually raise the entire setting of the practice, entire medicine as a field, and improve our outcomes. So what I've realized was that it was very difficult to capture that, because a lot of those things are, although written incredibly well in our notes, and in fact, physicians train, pretty much 50% of our careers in medical school learning how to write the notes, and then potentially refining a lot of that over the course of practice, getting it shorter, getting it more concise, almost all down to a single sentence in the impression and plan, right? Where you're actually able to convey that component of it. And anybody that picks up that note, they're actually able to know exactly what the patient is. And then a lot of the times is able to determine what is needed for the patient almost several steps ahead. That component of it I found incredibly fascinating. And if you went back and looked at some of history's greatest professors and most influential people, all you really have to look at is Sir William Heberden, right? Who really described true angina, what that classic angina was about. And that's 100 years in the making, and we still rely on the exact same thing. But yet trying to capture that in medical research, it is difficult. It's difficult for non-academician. Dr. Annabelle, you'll probably be able to tell us better how we can actually do that. But these transformer models was literally a breakthrough for me, in that we can now capture those things much more better, because it actually can read your notes. And not only can it read your notes, but it can actually apply probabilities and weights to factors inside your notes that we don't typically see, but it can actually increase the weights on the social determinants of health. It can actually even increase weights on things that we have never determined before. And so therefore, if we use these models to be able to run prospective trials, run the ability, what Malik was talking about was, can we actually bring the feedback and the what we find in these researchers, what we find in that is actually benefit in our implementation in medical practice, directly back to the hands of the physicians themselves? What would actually happen to the evolution of improvement? Can we actually get quicker with them? And I think these language models are really the beginnings of being able to do that. The second aspect of it is that we saw this happen already in computer vision, right? Particularly with Google Image. Google Image, with Vian and I have some in our background. We were developing the same technology just before Google Image actually occurred. And in fact, I said to Via, we probably should think about something like image search. And then approximately 2 years later, Google Image actually occurred. And it was because the development of the models came of age, where they're actually able to glean with pretty precise accuracy what was actually inside those images. It took a lot more work to get to the level of creating transformer models, almost 10 years. But we now have them. And in fact, in 2019, as we would benchmark these models, Stanford actually did a lot of the work on that. They've designed multiple different type of tasks to benchmark these models, two of which actually will be near and dear to us, including question and answers. These models are now able to do those tasks at a level that is just as good as human beings are able to. And a lot of that is actually because they're actually doing something slightly different from how images actually work. A lot of it is actually taking a lot of unstructured data and be able to train very, very large vector spaces with these sort of unstructured type data. And then as they begin to increase the size of the models, first starting with BERT, which was about 345 million parameters or 45 million weights, they have actually increased that now to about 1 billion weights. And once you get up to about 1 billion weights, everything that they've learned from the internet, and essentially what they did was they actually crawled the entire internet space. They were actually able to glean cause and effect, correlation. And so the amount of training data that is required for a new task actually goes down. And in their latest iteration, Google has now produced 1.6 trillion weights in their latest model. And what that actually does is that we've actually now go down from the amount of training data that we need for from a few hundred training data for a model down to almost 1 training data, almost to 0 training data. And these models will just know exactly what you're talking about. So case in point, when we first trained our initial models, we were actually running it through the USMLE questions and actually the board type questions. And amazingly enough, actually these models can actually answer these questions almost as well as we are. We need more data to actually beat us, of course.
Okay, now you're scaring me. Question for you. I have been noticing that, I've been in practice now for 31 years. I've been a cardiologist and concentrated on women and heart disease. And what I find frustrating is that women tend to have a lot more abnormal EKGs because they put the leads in all different places because, the breaths get in the way of getting an EKG that was modeled after men. And so is there something we can do to improve diagnosis of MIs or ischemia in women where you have so many configurations of the chest? Can AI do something about that? Now that we have troponins that are so sensitive to finding injury, we should probably create a study to study what is ECGs that's suggestive of ischemia or myocardial infarction in women compared to men. What do you guys think about that? Can AI help with something like that? Anyone can answer. Molly,
we know that women are undertreated. In acute MI, in heart failure, they're undertreated compared to men.
Which leads to increased mortality.
Absolutely.
Yeah.
They have worse outcomes.
Yeah.
And, the fact that women have breasts, and by the way, very obese men also have a similar problem with ECG lead placement and consistency. ECG leads are not geometrically related. They're anatomically related. Where V2 and V3 are on me could be completely different on somebody much bigger or somebody with large breasts. So you're right. I think that's a ripe area where a more precise personalization, and there's been a little work done. That is, why aren't we using AR, VR to assist people in appropriately selecting the lead positions for an individual? I think that's a great application because it's dependent on your chest. So we've got these incredible, supercomputers with very high resolution cameras. There's no reason why EMTs couldn't put leads on appropriately for anybody in a personalized method. I think it's a great research project.
Yeah, I think just to add to that, I think the most important question, in my mind, is trying to break down the treatment gap or that clinical outcomes gap into what aspect of that is in terms of diagnostic, like missed diagnostic errors, right? Which is where something like the example Dave just gave comes in. Mm-hmm. Then there's sort of like the sort of disparities of care based on just pre-biased notions and bias that comes into acuity of illness or symptoms or what have you for acute MI versus heart failure, other things like that. And then there's the just treatment gaps in terms of just practice of medicine. And I think there are different ways technology generically used can help with each one of those. And I think we need to just map, and not everything's machine learning or AI, but the different digital tools can absolutely be used across the entire continuum of gaps. But trying to right size what is the actual need and solving that problem uniquely is probably the way to go. On the diagnostic side, to Dave's point, yes, maybe it's about lead placement. Maybe it's about ECG interpretation is incorrect. Maybe this idea of reduction of practice to everything being STEMI or non-STEMI. Well, we all know from a physiology perspective, it's not, those are just the surrogate biomarkers of physiology, right? Maybe everybody knows in medical school, like 10 to 20% of MI is missed because of this ability to only do reductionist practice of medicine, which is pattern-based as opposed to physiology-based. There's all sorts of these things. I would love to go back to 1950s and say, because of data science, machine learning, can we do vector cardiography now and not pattern-based recognition? Because we have the ability to do that, whereas we had to simplify things along the way in the 80s and 90s, right? So I think there's other things you can do now much better that talk about the deep physiology as opposed to this, right? So I think that's the way I would think about the problem.
That would really be an innovative, just a disruptive innovation to, instead of EKGs, use vector. And now with the HS troponin, you can really hone in the ones who are having myocardial injury and send home the ones that are not. So I think we have so many exciting things that we can still see in the care of people with heart disease. I'm going to turn to reinforcement learning. How is that different from machine learning? Oh, by the way, for the audience, please ask your questions because we want to hear from you and we want you to have the opportunity to ask these brilliant minds the questions that you have in terms of cardiology and AI. So please put in your questions in the chat box. So Viet or Roger, can you tell us about reinforcement learning and how that's different from machine learning techniques?
Yeah, you want to take that? Sure.
Yeah. So machine learning and reinforcement learning, with machine learning, it is looking at the different mathematical algorithms, ways in which the neural networks would learn. They are all optimized for various different modalities. For example, convolutional neural networks would be great for image recognitions and view trained models and stuff like that. But it doesn't really have a feedback loop. This is where reinforcement learning is the extension where you are feeding information back to the AI for it to self-evaluate its models. And so with that approach, then the AI can say, okay, here's what I propose is based on my training and with the output, and you have a monitoring of for example, patients. This is what Dr. Alberts does with this technology, brings it back, and then it's self-evaluates. So they're kind of one and the same, or they support each other to give a complete feedback loop.
Okay.
Yeah, I'd like to mention just briefly is that I think that solving that game of Go, where Google actually beat one of the world's best champions in Go from Korea, was probably an eye opener for me and actually many of my colleagues here in Seattle. And when you're actually able to do that, you really see a parallel because apparently I hadn't studied Go very much, but what I do know is that the number of board positions are more than the number of atoms in the universe. And that's very similar to medicine, is that there's almost infinite possibility. And what Tatiana was saying really is that when she studied her opponents, I see the exact same thing that I do for every patient that I come in. I'd spend 15 to 30 minutes just understanding them, even though the chief complaint is just chest pain. It's because even though the diagnosis is the same for all these patients, there is tremendous amount of clinical variability in the setting of the presentation, clinical variability in terms of their response to treatment, and also clinical variability in the outcome aspect of it. So when Viet and I were just finishing up our project at the NIH, we had learned a lot. We learned how to do gradient search. We learned how to do our sort of limited version of supervised learning at the time. And there was really nothing like machine learning at the time, but we knew we loved AI. We were really passionate AI, and we wanted to go to the next level. And I was studying for my board exams, the step 1, step 2. And the last thing you want to study is actually the books, right? When you're doing that, so what you're thinking is usually artificial intelligence. And it dawned on me, we were working with Meditech at the time, right, which was a relatively primitive electronic medical record system. I probably shouldn't say that because they're actually still here. But what it was is very similar to the computers, the older computers that we were using, right? The Tandy computers, the Apple II computers, is that they were so simple. And it was really designed for developers. And in the Meditech space, it was really designed for you and I, right? It was the very beginning of digitization. And that was able to inspire what I thought was the next step was that what platform out there, what single focal point out there allowed us to be able to connect the input of the patients, right? Where the patients come in, where the physicians would describe them, where the labs would go to, and the actual outcomes. And it was the electronic medical record. It was essentially Meditech, because when we followed up with those patients, right, we get the lab data back. We saw what happened to the statins, that the statins reduced the LDL. And I was talking to my mentors at the time, because if we can somehow create that loop, right, where we can connect them, and it was hard at the time, right, we could do the outcomes. What we couldn't do was we couldn't do the representation of the patient, because the representation of the patient required language. You could do labs, you could do EKGs, and I'll talk a little bit about that EKG because I think that inspired a moment there. But you could do imaging, because we could do imaging at the time, but the language was still very hard. And the key was, if you can connect those two things and give back to the physician what the computer thought the next step would be, what would be better in terms of the treatment the next time you saw the same patient, then the doctor would make an appropriate choice and guide the algorithm to actually get better. And guiding the algorithm would get better would allow the algorithm, again, to rethink the next phase of moving. And that's how I think reinforcement learning is different from that of the typical machine learning algorithms. They're both out there, but I think in healthcare right now, what we're doing is we're really just catching up on the initial supervised learning model, except for if you're Malik, which I can clearly tell he's already have seen right past down to it, the completion of the feedback loop. These machine learning algorithms have the ability to guide from input to output in a very direct path. So, and in fact, not only that too, it really doesn't matter what modality of data actually comes in. So you can actually fuse the troponin with the EKG. So if you have EKGs and troponins, the way they represent them, so what these machine learning algorithm really does is that it breaks down the EKG into fundamental 2x2 squares into convolutional neural networks. And then essentially what it does is it recombines them in typical regression mathematics, right? More complex regression mathematics, but essentially regression mathematics. And then it combines it in a way until it finds the right formula to be able to lead to the outcome. So Annabelle, for your question, incredible question is that if we can't get the answer that we want, we just basically increase the number of data points that we need, whether that is HS troponin, whether that is more EKGs in women, whether that is VR, right? Dr. Albert's thing was quite incredible, is that we would just change the way they do things. Then as the data comes in, these machine learning algorithms will begin to find better pathways and better ways to read that EKG.
Thank you. It shouldn't be that hard to do, actually. I mean, we can probably create a study right now. But Malik, did you want to add to that?
No, I think Viet and Roger covered it pretty well. I think it's okay. Let's move on to the next question.
Just as I think all of the speakers have mentioned, we need to take massive multidimensional data sets when we build models, and in ideal world, that will include all the things that have been mentioned in this question, meaning age and other things related to individual, but also, in my view, we will have to, in future models, incorporate genetics, and as we talked about, socioeconomics and all kind of physiological variations, along with data that we can get from claims data, EMR data, and everywhere in between. So the models that we're looking at are all inclusive. So if we look just at subsets of data, we can get reasonable results, but I highly doubt those will be the ones that will lead us to the future. And what I'm really excited about, once you start getting those 360 degrees of data in healthcare, we, for example, develop an algorithm that can generate hypotheses. So once you get into this exciting space, how we know what we don't know, right? And that can, that will bring us to a completely new level, because right now we operate from our existing hypotheses that of course is limited to our knowledge. And then when you get all the other data and start getting into identifying new hypotheses, we might be able to have breakthroughs like in this question for specific type of patients that we're looking at.
Yeah, I mean, it's similar to the question about women, because it's really personalizing medicine to fit that particular person. If it's a large man or if it's a woman with large breasts that you can't even get the leads in the right place, that is a really important question.
And just to add to this, just to add one more point. When you're looking at this specific thing, like you mentioned, certain body composition that impacts the way you diagnose, I think super new technologies such as metaverse can be real instrumental in teaching students on how to do certain things on certain types of people. So metaverse is kind of completely new thing, but people, who have been playing with Second Life. And so I think those technologies like Dave mentioned, AR and VR, but you take it to the next level with metaverse, will bring us to the point where we will teach, students in medical schools on how to apply and use certain techniques for specific audience, especially like you mentioned with placement of EKG on certain body types of people.
So I'd like to add that, sorry.
Go ahead,
Viet.
Okay, that artificial intelligence and AI, it really focuses on cause and effect, right? It doesn't understand the pathways of medicine whatsoever. It just looks at through millions and billions of data points. It sees cause and effect, and through all the mathematical statistical analysis that it builds. But the cause and effect is optimized for the existing drug. And only up until recently, most of the trials were done with male and white, right? For example, pain meds, right? It's only been recently discovered that the female pain pathway is completely different than that of the male. And so you got anesthetic such as Tylenol and ibuprofen, which actually really optimizes for male pain, but not so much female pain. And so when the same thing with all these meds that you have, it has to connect back to the pharmaceutical research to differentiate between male and female pathways as much as it does the cause and effect. So to truly optimize for the maximum effects, the most optimal path for treatments, be it a child, male, female, what have you, you have to connect from the clinical trials, what physician sees, what the patients are exhibiting, and then bring it back to the farmers, right? And it has to be a full, complete loop.
Thank you. Dave, did you want to add to that?
Yeah, I hate to be the bearer of cold water, but unlike Google crawling the web, health information on adults, certainly on children, is very private, very restricted, legal protections all over the world that are not consistent. And so the development of these huge annotated data sets will be a challenge. There was a question, who's going to fund this? Well, we know Google's funding a study called Baseline. It's being held at Duke and at Stanford, with deep resources to try to gather data. A lot of people don't trust Google. DeepMind got into big trouble with the NHS. So I think we're going to have to be very cognizant of the fact that, everybody's worried. What if my insurance company finds out I've got AFib? What does that do to my rates? What does it do to my insurability? We didn't, it wasn't very long ago that would have precluded you from getting life or health insurance, precluded you. We only changed that in the 2000s, people. So I want to say that the development of these databases will not be as easy as ImageNet and the challenge. We have other very important challenges. And when you talk about children, infants, we want to protect them. And that includes protecting their data. So, it is going to be a challenge. It will be all funders, NIH, which has dramatic rules. And I think, we will proceed with caution because I think there's no other way to do it when you're talking about people's health and their information.
Good
Yeah,
point.
there's a great point, David. And maybe I'll just add a couple of comments there, Annabelle, if it's okay.
Yes, of course.
That, somebody also asked a question about somebody's a trainee in MD, PhD
Yes.
program right now. So I think it's all connected, which is that in order to build really accurate and scalable ML models for clinical use, I think to Dave's point, there's a number of components, part of which is data collection. And we want the right heterogeneity of populations to collect the data from. But then there's a part of data annotation. So as we know, garbage in, garbage out. Somebody's got to annotate this data. So there isn't a single company or institution in the world that can do this all alone. So my point being, it's an ecosystem play. When we talk about who funds it or who benefits from it and who's involved in it, I think we have to make sure that it's going to be a number of different individuals and entities that have to come together to make sure we can support the development and validation of these tools that can really get the kind of widespread adoption we need to see impact. In pockets, this can happen at a Google, it can happen at a Mass General or Cleveland Clinic, but to really get widespread adoption is going to have to be an ecosystem, because otherwise it's just the model's as good as the local model you built it on, and it's just not scalable. And nobody's studying these things thousands of different times in clinical trials to say, does this model in Boston work at model in Oklahoma, right? So I think we have to take a broader view, and maybe NIH is the convening body, but some other, we'll have to think about the ways different groups come together, really do this at scale. That's sort of the one plea and one, as the AHA thinks about this, and how do we think about that?
Does a model in Sweden work in Nairobi or Beijing?
Good question. I think Roger wanted to chime in here.
Yeah, no, that's a great point, Dr. Albert. Word of caution heeded, and Malika, I love that answer. We've learned a few things. I think the first thing is that unfortunately, even though we are the gatekeepers of the patients and the data and the resources, actually, imagine the amount of resources that's going into doing these tests for the patients and the outcome. Other companies and so forth like that are going to do it, right? Google, they're going to do it, and so. The way several of my friends, really, really great colleagues of mine, have said to me a long time ago is just that, we get involved. I think that's the most important aspect of it is that we get involved. And I think one of the things is that it is hard to find ML people, as I've learned. We had a group of people that joined us for a competition, almost about 1,000 people during the initial parts of COVID-19. We had a hackathon. And I could say only a very small number of them can actually do ML. So I think the beginnings is really taking a very proactive approach and get involved, particularly at the medical school level. And I know the deans are doing it. I know all medical schools are doing it. I know Peter's doing it. Peter Noseworthy from Mayo Clinic are doing it. And these are incredibly the great beginnings of actually putting that type of skill level and ability that's actually needed inside our entity. Now, with that said in mind, the second aspect is that I've seen something now that is quite incredible, and I think Tatiana has probably already seen it as well. Is that the encryption space and the cryptography space has been rapidly and parallelly developing and evolving at the same time as ML has been. And in fact, because the amount of sheer finances that are going into it, I would say that they're actually a little bit farther ahead. But the one of the things that I've seen is that, to go back to your question about the Swedish question, can you apply the models in Sweden here? It turns out that one of the architects of Silicon Valley, and I published it for his PhD thesis, was really a technique known as federated learning, right? So federated learning. And in fact, it was incredible when I first saw it. I couldn't believe that it actually works, because we were actually doing it in games and then subsequently doing it, trying it in people. is that it's an ability for us to transfer the experience from one model to the next. Now, imagine if we try to say that between humans, right? Like, a cardiologist transferring knowledge to another cardiologist is essentially a curbside or potentially a second opinion. Or, if we could take it a step further, it's essentially cath conference, right? At most, our bandwidth is about like 5, maybe 10, 15 cases in cath conference, right? If it's an M&M. But so it's very limited in the ability to transfer this knowledge. But with federated learning, you can take an individual model and you can learn from the local area, right? Like, whether it's cardiology that you want to learn, or whether it's the female's EKGs that you want to learn, and it accrues the knowledge on that specific type of data. And then what happens is within the weights, not necessarily in the data actually can remain inside on-premise servers. You actually can transmit the weights across to another model that is maybe in a different area, or maybe have also similar expertise that you want to increase the performance by increasing the experience. And you can just do that by using this approach where you're actually able to take the weights and fuse them together into a single model. The resultant model actually has a higher accuracy and a higher report for that particular task that you're actually getting. And so therefore, what I see potential in the future, which is, by the way, this analogy has now been done with your keyboards, right? So Google Keyboard essentially does the exact same thing. It takes regional data, and because the keyboard is so sensitive in terms of what you type, the privacy that is involved is so sensitive that they're not transmitting the data in words. They're transmitting the data in encrypted weights, right? And then you can fuse that to gain better performance. What I see here is that we could do that with institutions. We don't have to transfer the data. What we're doing is we're transferring the signal.
Glad that we were able to discuss different sex differences in cardiovascular disease. And I learned from Viet that there's sex differences in nerve pathways for pain. So I'm going to have to look into that, which makes sense. That's why women present differently than men when it comes to different diseases, right?
Thank you for the opportunity for us to present how AI is applied. So hello, everyone. My name is Viet Le. I am one of the co-founders of Charisma. And today I would like to propose a new approach to how we can address atrial fibrillation, that is, employing bidirectional artificial intelligence to shift the current paradigm from a reactive response to a medical event to proactive care and early detection. But first, I'd like to invite Dr. Eng to share a story of how we got here.
Thank you, panelists. This has been an incredible discussion. We started our journey developing AI, and we actually went to India. Actually, in May of 2021, we saw an incredible plight and crisis. It actually, literally took down their healthcare system in India, and several of our friends and colleagues actually contacted us here in Seattle. They knew about our work in AI, and they wanted to see if actually we could help. And within about 2 weeks, we actually built our first AI agent that we can actually deploy to India that did risk stratification on some very simple metrics. And the metrics were on your phone. This actually allowed the physicians to be able to take an entire roster of their patients and monitor their patients in the community. And these are relatively high-risk COVID positive patients that would have actually required hospitalization if they were here in the United States. And it worked. It worked incredibly well because it allowed physicians to focus on the very high-risk patients, the one that could potentially progress. And also it allowed the nursing staff to be able to take care and look after and follow up on the low to moderate risk type patients. And at the exact same time, our AI engine monitored these patients sometimes twice a day and continually adjusting the risk and feeding back that risk stratification process back to the physician. This was our eureka moment. And I wanted to get a chance here to be able to demonstrate a little bit of what we built.
Patients enter the system by first receiving an SMS message. Click on the SMS message. The patient will be taken into the application. It is the usual review of systems. We're actually able to ascertain a comparison between the day before and actually the current symptoms to get a sense of which direction the patient is resting. Patients are presented with a classic review of systems, all the different signs and symptoms, and they can easily click on those fields and instantly be able to record them, very similar to how you would do it in clinic, except it's actually done on the patient's phone. In order to capture some additional clinical values, we present the patient with the ability to enter their vital signs. Most individuals now have their pulse oximetry, and if not, a lot of individual already has a blood pressure cuff. If the individual doesn't know how to do those things, there's a question mark that actually brings up the video that teaches them how to do that, which are taken from national medical institution websites. Once the patient completes that, they're actually able to take a picture of any lab values that they have had and be able to send that in directly to our system and our physician. After the patients have entered their data, most physicians actually have to see their patients linearly. Our system sees all the patients simultaneously. And therefore, all the physicians have to do is click on the category of risk that they're looking for. And it brings up the patients that have that high risk category. This is trained by a neural network, looks at all the different parameters, including vital signs and other metrics that you can give it to be able to make that prediction at an eyeball level. As we click on David Liu, one of the high-risk patients, we're actually able to see all of the things that a physician needs to see. What are their past medical history, their allergies and medications? What are their vital signs? Trended in a day-to-day category, being able to see whether they're trending up or trending down in the wrong direction. And additionally, being able to see their day-to-day symptoms as they have logged in the review of systems during their intake. We're actually able to see when the symptoms, again, day 3 or day 4 or day 5, and when the symptoms actually resolve. Looking at all of these things, you can actually put this directly into a machine learning algorithm and be able to make predictions from it. When you're seeing patients, one of the hardest things to get through is actually writing the notes. The notes are usually long, but even more important thing than writing the notes is getting the orders and getting the medical plan for the patient. So because we train the system to understand natural language, we're able to bring the language directly into the system and take the recommendations and the diagnosis directly to the fingertips of the physician. Here we can see that a patient came in with shortness of breath and swelling and is able to accurately predict congestive heart failure. It's because it has seen millions of congestive heart failure patients and know that this is the way to be able to treat them. We treat them with medications like Lasix, for which we can directly add to the orders for the physicians and the nurses to carry out, and also directly add it into our notes. We can document congestive heart failure into the system, and we can also document what the patient has. Medication non-compliance, high risk of coronary artery disease in a patient that has a family history of coronary artery disease, and potentially in a patient that's presenting for the very first time to the emergency department, it is also possible that the patient may actually be having acute myocardial infarction. A lot of these things will be required to be tested for, which the system is capable of doing. The system has already recognized the need for certain medications, including heparin, GI prophylaxis as well. Not to mention taking care of some of the mundane things such as bowel prep and bowel regimen. The system learns. Every time it sees a patient like this and sees physicians using these particular orders, the system will learn and be rewarded in the system for being able to bring up the best recommendations, the best diagnosis, and the best prescriptions.
So this constitutes an AI platform that is optimized through bidirectional learning. That is, the AI gleans knowledge through continuously monitoring the patient, and the physician learns from the AI through a feedback loop, a loop that starts with an encounter to diagnosis, tests, treatments, through to the patient's outcome and back to the hands of physicians. All the while, it continuously gains knowledge, understanding and honing its diagnostic skills from an ever-expanding number of physicians, patient encounters, and care outcomes. The AI learns from every data point of a physician's encounter and all of the nuggets of knowledge that are otherwise never recorded or shared using existing platforms. Through this reinforcement learning process, the AI continuously improves the GDMT treatment positions for dosage and lengths of treatments based on specific age, gender, ethnicity, weight, comorbidity factor, socioeconomic standings, and many other factors. Whether at the patient's bedside, in the exam room, or even in the patient's home, it captures it all, gleans trends and patterns that are otherwise missed in a current patient care model. Then it begins to build the means to understand patient's outcome even before diagnosis by ingesting the data from disparate sources and modalities. This helps the physicians create treatment models, permitting them to intervene even earlier in the progress of the disease. Needless patient suffering is prevented, countless lives are saved, and medical advances at an increasing pace. Now, I'd like to share a personal story. My wife, 2 open heart surgeries, 16 operations of both failed and successful ablations, and she has COPD. To this day, 43 years later, or 43 years of her life, has been challenging to find the treatments that are not contradicting the lung or heart function. So with a system like this, hopefully we can both advance pulmonary and cardiology treatments in parallel. So Working in the background, the AI continuously shadows the physician, learning and gathering raw data, analyzing the physician's thoughts through the notations, and all the while observing and self-evaluating its model based on the patient's outcome as the grounding truth. At that point, the AI has learned, further incrementing the precision of the predictive model. In learning, in the learning loop, as the learning loop continues, building piece by piece, step by step, this is our approach to deriving an atrial fibrillation predictive model. Without distraction, without fatigue, and without limits, the AI learns. So the neural network can learn at an unimaginable scale. It can take an enormous amount of data, identifying statistical meaningful patterns across millions of differential diagnoses and data points that would otherwise be indiscernible to the human mind and unseen by current technology tools. It can do this in near real time and provide feedback in near real time. It becomes a partner in the new paradigm of patient care with physicians and the patient. This is no longer in the future, it is now. It is said that, as Roger mentioned, pictures worth 1,000 words, and that's the one fact that made computer vision so powerful. In medicine, we have more than one picture. We have more than pictures. We have labs, imaging, and importantly, descriptions of the patient's gestalt and their symptoms. This provides one of the most comprehensive sources of assessments of the patient's risk for atrial fibrillation. We can use that to optimize our detection of atrial fibrillation, not within days, weeks, or months, but within a few seconds and delivered to the attending physician during a patient encounter. With our platform, we are leveraging the power of AI, an innovative machine learning process, and with high quality data to learn from, we can use AI to perform prospective validation through deep learning for better detection of atrial fibrillation. This will help permit us to move the needle to an earlier detection, testing, and treatment of AFib. Now, we invite you to join us on this journey. You can be part of this new limitless medicine of the future today. Let me turn back to Dr. Volkmann to open up for questions.
Thank you, Viet and Roger. Of course, I had to unmute myself. That was really awesome. I mean, it's really mind-blowing information that you just gave us. And I think Dr. David Leone also agrees in the chat box. This is excellent. Is this AI supposed to be a standalone EMR or a third party that links to the EMR? This is the question.
It can be in its own EMR, but it also works with Epic, an existing EMR system. Definitely.
Thank you. Roger, did you want to add something to that?
Yeah, when my brother and I are actually both physicians, my wife actually, she's a woman cardiologist, Dr. Vogman, and all of us feel that we should be taking a strong position, and taking care of the patients directly. And so this system was really meant to be able to stand alone as a doctor that can use the system to help patient care. And obviously, we want to be able to be bi-directional with the current vendors that are out there as well.
Well, I think you can use that technology that you were showing us that you used in India, which was truly amazing work. Congratulations on that. And I'm sure you helped thousands and if not millions of people in India, but we can probably use that technology for what we were discussing earlier. By not using smart monitoring for atrial fibrillation as a way to decrease the risk of stroke, but to actually teach people the feedback of what their lifestyle is causing them to have atrial fibrillation. I think that would be a great individual learning process for them. Can you do something like that? That's
correct.
Make sense.
It is a matter of identifying what factors to feed the AI. So at the moment, it is trained to absorb everything that's in the physician's notes, labs, drugs, and all that stuff. And so it's a matter of feeding patients other information. We have to identify what other factors you wish, right? As I said, gender, ethnicity, age, socioeconomic standings, even their nutritional content on a regular basis. What we found in India was that patients were more than happy to provide information. In fact, they actually wanted to input every 2 hours. And the physician was saying, hey, no, please don't do that.
Too much data.
Too much, well, not just too much data, but they want the ones who's helping the family member to actually rest and not get exhausted, because it's a marathon, right? It's a 14-day marathon that they are going through. So we actually had to limit down to 2 times a day. And that was more than sufficient information to capture patients standing and adjust in real time. So so yes, we can definitely feed more information. It's a matter of doing the trials.
Thank you. I think we have time for one last statement from Dave Albert. I was going to ask him, can you give us a hint on what your secret inventions are that we should be looking out for in the future?
Well, 10 years ago, I started off with a personal single lead ECG, and today we have half the 12 lead ECG, all 6 limb leads. Where do you think that trajectory is going?
Got it. Thank you. I think we can work on this with the myocardial infarction, huh?
That sounds like a good plan.
That's wonderful. I don't see any other questions. Do you have any last words? Why don't I give each one of you a last word to tell our audience, what made you excited about AI and what you think the future will hold, and how we can decrease cardiovascular disease in men and women and change the trajectory of this mortality. So Malik, maybe you can start.
Sure. I'll be brief given the time. So I think all of us will agree in this panel, I'm sure, that there's an incredible amount of excitement and opportunity that lies ahead in using data science and machine learning for improving cardiovascular care. I think the question really is, how do we work together as an ecosystem to actually get the right data sets and validation plans in place to actually do this, where we can earn the trust of practicing clinicians to deploy it. I think the biggest challenge we'll face is we may build great models, but if we can't get people to adopt them, we won't see the impacts. I think that's the gap we want to fill going forward.
Thank you. Dave?
Well, I think we have great opportunities to augment caregiver, and I don't just mean physician, certainly not just cardiologists or electrophysiologists, but healthcare providers at all level, all the way down to the home. And AI will be that curbside consult that provides you insights into taking better care and getting better outcomes.
So exciting. Roger and Viet, any last words?
Yeah, I was just going to say, data is exploding at an unprecedented rate, and AI will help us process that and distill it down to actionable knowledge for physicians and patients, and that we are all in it together. We should all work together to find better solutions.
Thank you.
Roger?
Roger?
I love Malik's statement about building ecosystems and communities. That was incredible. And we learned something very similar, is that when there was a plight, there was so many people that came together. And I want to give a shout out to the UC Berkeley team that developed the Ray. Without them, the ability to do sort of distributed machine learning would not be possible. But again, the community there was incredible.
Thank you. Very brief last word, Tatiana.
I would just say there are like few P's. So where AI can take us. So first of all, we mentioned on the predictive side, very important. So we can see, healthcare future or disease progression and hopefully prevent it. That goes to the second P, preventive. So we need to focus on personalized recommendations that will prevent getting disease in the first place. Personalized AI will most definitely help us with precision personalized medicine. And the last point I want to bring is holistic, because people have multiple different conditions and everything else. So we have to look at the whole patient, the whole environment, and AI will be able to bring all those dimensions in.
Love that. after all the machine and artificial intelligence, it all boils down to being holistic. Meditate, 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 right? Thank you all. It was really a wonderful panel discussion. I learned so much, and I hope we can continue to make this conversation about improving cardiovascular health for our patients. So thank you all for being here. It was great to be working with you.
Thank you.
Thanks, everybody.
Thank you.
Thank you.
Bye-bye.
Bye.